Hello, we are Maria Eugenia Galina, Alejandro Gonzalez, and Shina Casone. We are Team 11, and we will present the sixth delivery of our project, Estimating Obesity Levels Using Regression. The hypotheses we selected to adjust in order to practice the regression analysis include the categorical variables gender and physical activity per week, and the continuous one body mass index or BMI. The BMI is defined as the weight divided by the square of the heights. The first original null hypothesis we will work with states that the average BMI in males is smaller or equal than the BMI in female subjects, and the alternative is the average BMI in females is smaller than the BMI in male subjects. Notice that with this approach, we are comparing mu's of the variable BMI. Here we can see that the BMI follows a log normal distribution and the gender has a binomial nature. To work with regression analysis, we need to reformulate our hypothesis. We will consider the average of BMI as our dependent variable y, and gender as our independent variable x. And we establish the BMI as a function of gender. So, y is a function of x, which is multiplied by a beta coefficient and some error factor seen as well. This is the formula for a line. Then, we reformulate our null hypothesis. It states that the gender of subjects does not have an effect on their body mass index, and our alternative hypothesis says that the gender of subjects has an effect on their BMI. These hypotheses are expressed using the coefficient beta. If we want to state that the gender doesn't have an effect, it should not be a part of the equation. So if its coefficient is 0, the variable will be removed. And on the other hand, if it does affect the dependent variable, should be present and the coefficient has to be different than 0. To select the regression model to use, we consider that the dependent variable is a continuous one. So we will use linear regression to perform our analysis. Also, our independent variable is categorical, so we could encounter problems of multicollinearity. To deal with this, we will use the Rich and Lasso regression. And finally, we will use GLM to compare our results.
In order to make the Ridge and Lasso regression models, we first declared our response vector y1 as the data of BMI and our dependent variable x1, which is a gender labeled as 0 for female and 1 for male. For the Ridge regression, we declared a grid of different possible lambdas to try the model with, going from 10 to the minus 2 to 10 squared. This grid had 100 lambdas. In order to choose which lambda was the best for our model, we performed a cross-validation method already implemented in the GLMNet package. In the Lasso regression, we used the same response-independent variables. The grid is slightly different, going from values of 10 to the minus 5 to 10 squared. And just like the Ridge regression, a cross-validation method was used to find the lambda that had the lowest mean squared error. In the lower part of the slide, you can see both plots of the lambdas and the mean squared error of each of the models. Knowing which was the best lambda that resulted in the lowest mean squared error, we then computed the coefficients for our Ridge and Lasso models. Here we show the lambdas used, the depth ratio, and the null deviance. It is quite clear by looking at depth ratio that adding the beta coefficient to our model does not seem to really improve the null model. The final model with the coefficients obtained is shown at the bottom of the slide. In this case, the intercept was necessary for our model, as it represents the mean of the BMI of females, while the sum of the intercept and the coefficient would represent the mean of the BMI of males. We then computed a generalized linear model to compare some of the results obtained previously. As we can see, the intercept value and the coefficient obtained are not really that different from our previous results. The deviance residuals show a skewness, which means that the model is not a very good one. We can also see the null deviance, which is basically the same as the one obtained before, and the residual deviance. The residual deviance is slightly smaller, which means that adding the coefficient to the model improves the performance, but not in a very significant way. All of the regression models apparently show that the mean of BMI of males is larger than the BMI of females, which would reject the null hypothesis. But nevertheless, the residual deviance from all models show that the regression model is not a very good one.
In contrast to the regression results, the Fisherian Bayesian results can be analyzed with the former statistical hypothesis. On the left, the Fisherian results show an overlap between the female and male plots, which does not allow to reject the null hypothesis of males having a lower or equal BMI average. Likewise, on the right, the results from the Bayesian posterior distribution cannot reject the null hypothesis because of the overlap. However, the tendency is the same for Fisherian, Bayesian, and regression results. It is noticeable in all approaches that the BMI tends to be larger for males, even if the plots overlap in the Fisherian and Bayesian cases. The second scientific hypothesis states that the excessive use of electronic devices and lack of physical activity can be associated as a factor to increase the BMI of people. Its statistical hypothesis states that the null hypothesis, subjects that do not perform any physical activity, FAF, have a larger or equal body mass index BMI average than subjects that make some physical activity. And its alternative hypothesis states that subjects that do not perform any physical activity have a smaller body mass index average than subjects that make some physical activity. The variables involved are the BMI, which is continuous, and the units are kilogram over meter squared, and the FAF, physical activity, which is categorical, 0, 1 or 2 days, 1, 2 to 4 days, 2, and 4 to 5 days, 3. However, for purposes of grouping the BMI data, the physical activity per week variable, FAF, is now in two groups, no physical activity and some physical activity. Since we can consider each subject an independent event, this variable should follow a binomial distribution, as we see down below. Now, the statistical hypothesis is modified for a regression analysis. First, we will consider the y as the average of BMI, x as the physical activity per week, 0 or 1, y is the function beta x plus epsilon, and well, we assume that the mu BMI is going to be equal to beta multiplying the physical activity per week plus epsilon. Then, the statistical hypothesis is divided in two. The null hypothesis, which states that performing any physical activity does not have an effect on the BMI of subjects, and the alternative hypothesis, which states that performing any physical activity has an effect on the BMI of subjects.
To make the ridge and lesser regression models for this hypothesis, we first declared our response vector, y2, as the data of BMI, and our dependent variable, x2, which is the physical activity labeled as 0 for no activity and 1 for activity. For the ridge regression, we declared a grid of different possible lambdas to try the model with, going from 10 to the minus 2 to 10 squared. This grid had 100 lambdas. In order to choose which lambda was the best for our model, we performed a cross-validation method already implemented in the GLMNet package. In the lasso regression, we use the same response and dependent variables. The grid is slightly different, going from values of 10 to the minus 5 to 10 squared. And just like the ridge regression, a cross-validation method was used to find the best lambda that had the lowest mean squared error. Just as before, now that we know which was the best lambda that resulted in the lowest mean squared error, we then computed the coefficients for our ridge and lasso models. Here we show the lambdas used at the def ratio and the null deviance. We can see that the def ratio is quite low, so this means that adding the beta coefficient to our model does not seem to really improve the null model. The final model with the coefficients obtained is shown at the bottom of the slide. Also in this case, the intercept was necessary, as mentioned previously, because it represents the mean of BMI of subjects that have no physical activity, while the sum of the intercept and the beta coefficient show the mean BMI of people who do perform some physical activity. Just as before, we also computed a generalized linear model to compare some of the results obtained previously. As we can see, the intercept value and the coefficient obtained are not really that different from the previous models. The deviance residuals show a skewness, which means that the model is not a very good one. We can also see the null deviance, which is basically the same as the one obtained before, and the residual deviance. The residual deviance is slightly smaller than the null deviance, which means that adding the coefficient to the model improves the performance of it, but not in a very significant way. All of the regression models apparently show that the BMI of people who have some form of physical activity is lower than the mean of BMI of people who have no physical activity. So, in a sense, we could reject the null hypothesis. Nevertheless, the residual deviance from all models show that the regression model is not a very good one.
Once again, we compare the regression results with the Fisherian Bayesian results. Now, the null hypothesis states that the BMI average is larger or equal for people who do not perform physical activity. For both Fisherian and Bayesian results, there is an overlap in the plots, so the null hypothesis cannot be rejected. Nevertheless, again, all of the presented approaches, Fisherian, Bayesian, and regression, tend to say that the BMI average is lower for people who perform physical activity. So, despite the differences in the methods, the outcome is fairly similar.